Thank you for joining. Thank you for spending a little bit of time on your Friday with us and RockBurst Technologies. My name is Kyle McCall. I am the Director of Commercialization Services and Member Relations with the Mining Innovation Commercialization Accelerator, and very excited to be working with the folks here at RockBurst Technologies and to help them to help promote this great study that they've got ongoing and to have them share a little bit more about information about what they're doing and what their technology allows. And I'm sure lots of folks here are interested in what they've got going on. Real quick, MICA, we support the commercialization of new mining technologies into the mining industry. And we've done that through a funding program, some commercialization services, and a kind of a network platform that you can leverage to promote your business and your solution. And thrilled to also say, RockBurst Technologies is also a recipient of MICA funding. So again, very excited about the technology that they're developing here, and that we have such a great audience to learn a little bit more about them. So with that, I will throw it over to Oscar and his crew there to talk a little bit more about the study and their technology. So Oscar, over to you.
Thanks, Kyle. Thank you so much, guys, for joining us, from wherever you are, good morning, afternoon, or evening. We're here in Vancouver this beautiful day. We're going to be talking a little bit about, our tech. So we're going to be focusing a lot about answering questions and clarifying a few points about how our technology works. And then we'll talk really, we'll spend some time there in the tech and also in the study that we're running in collaboration with MICA, the University of British Columbia, and McMaster University. So let's start with, this is the co-founders of RockBurst right here, inventor Cliff Edwards, and COO Chuck Lee, myself, Oscar. We definitely welcome you guys, to this, our first webinar, and explainer in a way of our CO2 pulverization technology. In a nutshell, what is it that we do? We break rock with CO2. We promote tensile stress within the rock, and we break the rock from within. This is important, and I don't have to tell you guys, to this audience, but this is an important consideration given the fact that comminution takes up to 4% of the global electricity consumption. So that is one of the key major aspects in the mining industry, try to decrease that energy consumption as much as possible. We'll get into the details about what this second paragraph says. So we'll go over with the presentation. But we have seen early evidence of interesting benefits that this technology presents in comparison with incumbent technologies. Again, for this audience, you're pretty familiar with what you see on screen, but what we are trying to do is, in a way, replace mechanical comminution. This is a long-term objective, but nonetheless, we believe that this is the future of comminution in general, not just in the mining industry, but outside of the mining industry. Opportunity is huge, for all investors that are out there in the audience. This is at least a $30 billion annual global opportunity. This is a summary of what we normally present our key benefits in terms of what our technology can deliver. Energy savings, we have some early estimates of around half energy savings compared to ball mills and SAG mills. And Cliff, will explain a little bit more about, where exactly are we in terms of, these estimates. This translates roughly into potential to decarbonize the mining industry around 3 gigaton per year. This is considering that we use CO2 as a working fluid in our technology, and that CO2 could also translate potentially into carbon credits, because that CO2 gets sequestered in the tailings of our process. Again, you're seeing here early estimates, so please don't, hold me to this, not just yet, but very, very positive indicators of where technology could go in the future. The last thing, this is a dry by default technology, although we're introducing water to improve certain efficiencies in our process. Again, we'll talk a little bit about this in later slides, and you will have the chance to ask questions at the end of the presentation, by the way. Or you can just type your questions right now at the chat, and we'll take a look in the Q&A later. So before we get into how this technology works, this is a quick video that shows the innards of some of the prototypes that we already have. If you haven't seen this video, it's just 30-second video, but maybe we can have some commentary from the inventor of the technology, Cliff Edwards himself.
Yeah, this is a very basic animation just showing, introducing the rock into a sealed chamber where you introduce the CO2 into that chamber and you permeate that CO2 into the pores of the rock in a supercritical condition. And then you rapidly decompress the chamber, which causes the pressure to increase inside the rock versus outside and fracture the rock. And thus you can turn your rock into your product size, and out comes the powder. These are 3 generations of prototypes that we've already produced and we've been using. The minimum viable experiment on the left was a very first rig, which just showed that this basic idea worked. The alpha prototype has been active for us for a few years now in the lab. It's what we use to run most of our experiments today. And the beta prototype on the right is our upcoming test rig, which allows us to test some different conditions for the process, some that may better lead to a continuous process than the batch processing that we've been doing with the alpha.
Yeah, so once again, just to recap what you just saw here very quickly, what we're doing here is promoting tensile stress within the rock. And this is an important aspect because, again, rock are 10 times weaker, 10 to 30 times weaker under tension than under compression. Again, for this type of audience, I'm pretty sure, you all know this, but using this thermodynamic way of breaking rock, we're basically taking advantage of that fact of nature in a way. Obviously, the devil is in the details in how to manage those thermodynamic levers that we have to move to get that breakage at the lowest energy threshold, easily achieved, relatively easily achieved in the lab. As you scale up, you have other nuances that we have to obviously take into consideration, and that is exactly what we're doing at the moment. But these are the 3 prototypes that we have at UBC, and you will see later down the road here that we have some results to show you in terms of what we have achieved for different types of ores.
We'll be using the alpha and or the beta in the mineral liberation analysis program and study that we're promoting here, and that those are the rigs that we'll use to do the comminution prior to doing the MLAs. This is a slide just to give you a little bit more insight into the way our process works compared to traditional milling. On the left, you've got the 4 boxes, A, B, C, and D going clockwise. So if we start with A, we show a particle with several features inside. One is a cavity, the mauve piece. Some are cracks. Those are the red lines, and some of them are just grain boundaries that have some porosity. And then in the next box, B, to the right, we show permeating with CO2, which works its way into the particle and through all those porous features. And then in C, we create, nope, on the right.
Oh, yeah. Sorry. Yeah.
So C, we create the tensile stress by rapidly lowering the pressure around all the particles at the same time. And then the stress is created from the pressure that's still remaining inside the rock, as the gas hasn't had a chance to escape at the same rate that we decompress around the rock. Thus, in D, we fracture the rock along all those porosity features. And then, if you want to zoom back a little bit, guys, you can see the test process on the right-hand side, where we prepare and characterize the feed. We load it into our test rig. We run our operating system for the test rig and add CO2 into the chamber. We prepare a rapid depressurization valve in the alpha, and then we run the system and do a rapid depressurization in the bottom left there, and then we vent the gas at this point. Later on in commercial systems, we won't vent the gas, we'll recycle it. In this case, in the lab, we're venting the gas, and then we retrieve the sample, and then characterize the results, the breakage results of the sample.
Yeah, one thing that probably we should mention at this point, this is obviously a batch approach that you're seeing here in our alpha prototype. However, we're studying different ways of converting this batch process into a continuous process. And the beta prototype is, the next generation prototype that, I showed in the previous slide is allowing us, to test certain aspects of continuous processes. So just to mention that, this is an evolution of how we see this technology progressing. So a couple of aspects that, Cliff just mentioned, the rapid valve that is needed to depressurize the system could be morphed into some other way of depressurizing the system in a continuous process.
Right. And this is an example of some feed and product that we've run through our tests in our prototypes. So on the top left, we have a commercial copper example with a bag of the feed ore size. It's 1.7, 2.36 millimeter, and then the bag products after running the tests on the right. And you can see, significant amounts of fracture of the different size fractions there. We've run platinum through our process on the top right, and you can see the feed size on the before, relatively large size. And then again, we've got, 4 reduced size fractions that come out of the combination process. And then in the bottom left, we've got limestone, a softer material that this is a very early picture from a number of years ago when we were just, I think, proving out our first test rigs. And these examples are just showing one cycle of our process where you put the feed in and you do that one breakage, a rapid depressurization breakage cycle, and you produce a certain amount of fracture across the size ranges, but some of that fracture is going to be at the product size that you want, say sub 100 micron. And then the oversize, of course, goes back in for another cycle. And in the bottom right, we have an example of a number of those materials that we've tested, including copper, platinum, limestone, which can represent any carbonate material, nickel, and copper uranium ore. And very recently, we've been testing also with kimberlite to extract diamonds.
So you want to add a little bit of detail on the diamonds aspect, why our technology might be quite useful?
Well, yeah, I mean, our technology, we obviously have this hypothesis, which is supported by literature for tensile breakage, that minerals will break along grain boundaries, and thus you can liberate those minerals very cleanly along all their different grain boundaries. And of course, that applies to all these metal types, but specifically for diamonds, there's a concern in the industry of breaking the larger diamonds in the milling process. And so obviously for value, you want to keep the large diamonds as large as possible as you're doing the extraction. And current milling processes risk breaking those larger diamonds. Our process, however, would tend to release the diamonds at their natural size, no matter what size they are. And thus you would, retain all the value of those larger diamonds. This is an example of particle size distribution charts for, to back up the pictures of the products that we produce from the feed. These are intended to show our breakage performance. These are showing individual cycles. So each chart has a black line which shows the feed size, and these sizes are all produced by taking first the feed, the black line, and then the products, the colored lines from the tests, and putting them in sieving machines and sieving them at different sieve sizes so that the particles can be, the mass of the particles that pass through a certain sieve size can be determined and then charted here. So you've got sieve size on the bottom going from, in millimeter scale from 0.01 millimeter, so 10 micron, all the way up to 10 millimeters. And then on the vertical axis, you've got cumulative passing. And that's just a common way of saying the mass of material that passes the sieve at that size. So in this case, the feed was obviously 1 millimeter to 3 millimeters. in size at 100%. And then the products from each of these 3 test cycles show that if you were targeting, for example, say a 100 micron or 0.1 millimeter on this chart size fraction, we're getting 40% of the massive material passing that size pretty much for each test cycle. And so the way the industry typically uses a single number to represent how much breakage or the size fraction of material that you've broken is using P80. And the P80 is the 80% line across the top of this chart. And so if we were to take this material and produce a P80, say at 0.1 millimeter, you can see that we only need to run it at 2 cycles. So we get 40% breakage in the first cycle and 40% in the second cycle would produce, 80%. So that shows, for limestone, we're talking about 2 of our pressure cycles to break that material down. And then the next chart is a copper example. And in this example, we've got the black line again showing the feed. The feed was actually 1.7 to 2.36 millimeter. It tapers off because the sieving itself produces some small amount of fine fraction. So you can ignore that long tail on the black line there. But the colored lines here represent 2 different test rigs. So the blue line is our alpha test rig. It's an earlier test that we did with this material, showing about 2% cumulative passing at 0.1 millimeter. And then we show results from our beta apparatus on the same material, and you can see that it's like pretty much a 10x improvement in breakage performance. So this is, partly to give you an example of the comminution performance we get per cycle, but also to show the progression that we're getting with our generations of equipment. And the beta is not the end. We will continue to optimize and push these numbers up. It's a bit hard at this moment to translate this into this slide into energy comparison with traditional means, but we model these results through a thermodynamic model we have of a sort of a conceptual process at a larger scale, and that's where we're coming up with our estimations for energy. So the last one here is copper uranium ore, very hard ore, quite challenging to break. The feed looks like it was essentially 1 millimeter to 3 millimeter roughly. And again, we've got an old test apparatus with that bundle in the middle of colored lines showing about 2% breakage at the 100 micron size. But then we've showing also the beta results at the around the 10% mark. So in other words, again, with this one, to reach a P80 of 0.1 millimeter, you would need to run, say, 8 cycles, and that would push that up to the P80 mark. And for us, when we run these number of cycles and the pressure and temperature and so on through our thermodynamic calculator, we can see, what looks like very promising energy results.
Just to summarize, what we have observed experimentally, and as Cliff mentioned, extrapolated, based on the simulations that we're doing, in terms of how we compare with compression-based comminution. This is what you see on the screen. In terms of CapEx and OpEx, again, too early to tell. However, the early estimates really point potential future CO2 pulverization mill at kind of the same level in terms of CapEx with, say, a ball mill, but a lot less OpEx. And this is because, we get rid of grinding media. It's a grindless comminution, what we are offering here, to be honest. Again, electricity consumption would decline. This is what we expect to see in large, scaled up systems. Devils in the details, we still have to work with our engineering partners, to make it so. And then you have, once again, dry comminution is the default mode of our technology. And there is the potential for carbon sequestration from our side because we use CO2 as a working fluid. Okay, so just really briefly, this is a snapshot of what we have done, or from the beginning till now. This is where the quick snapshot in a way. So we were funded initially by Natural Resources Canada, and we have continued working with partners, clients, and sponsors, some of them listed here, as we are now entering into the product design stage, which basically means working side by side, in this case, we're working with BHP as part of a technology development program that we have been invited to participate in for designing the first pilot, on-site pilot that we can deploy and start testing all these claims that you're seeing on the screen live in a real world operations. To get there, we need your help. And that's why we're running this mineral liberation analysis. But we have other aspects that we still have to fully understand and fully develop. And that's just the reality of when you're developing a breakthrough technology like this one. And what you're seeing here is basically the timeline, the pathway, the roadmap of all the other aspects that we need to de-risk to get a proper pilot design. And this will happen this year and next year. Again, asking for your help. This is the reason why we're running this crowdfunding mineral liberation study. 3 main objectives. Obviously, we want to validate our technology for liberating valuable minerals contained within ore in an easier way. Cliff mentioned a little bit about the aspect of the kimberlite and diamonds. Breaking our technology showing evidence of breaking along grain boundaries. So we want to test that with a whole plethora of other ores, and that's why we're asking your help to participate in this study. Obviously, this will lead to optimizing mineral liberation the way we kind of see and understand it. But we want input from the industry. Again, this is a crowd-funded approach. Again, not really sure, this is something that has been done recently in the mining industry. Our experiments are quite expensive, and we have engaged certain mining companies, but we understand that in order for us to go out and reach out to as many interested parties as possible, we need to run it in this manner. So this is the methodology for the study. Very simple. We're going to be receiving some shipped samples coming from mining companies, and we will develop basically a baseline comminution with either a ball mill or an HPGR technology, so we have a baseline to compare to. And we're going to be basically proceeding to process that ore that we receive with our own technology. That will be sent out to McMaster University. They are going to be the ones doing the mineral liberation analysis. They have all the nicer toys over there. And then we're going to be basically working on 2 reports. So 1 full detailed report per participant, and 1 library aggregated and anonymized data report sent out to all participants of this study. And then we will have a post-study opportunity for those who are interested in knowing whether we're actually saving either energy or potential GHG reduction with their ores. This is obviously the buy now slide, but why would mining companies will participate? We have certain perks, of course. You will have access to exclusive data, as provided in those 2 reports that I just mentioned. You will have the opportunity to dictate what goes into this technology potentially. Getting some feedback and input from the client, from you guys, will be absolutely crucial for us. Again, this is a new technology. So if this technology works, could be quite consequential for the mining industry. And we will need to work with clients and partners, to help us, develop the best they can. You will have priority in terms of, technology rollouts in the future. And you will also have option for customized analyses. Obviously, we will provide, number of shout outs to you and your team as an innovation supporter. Again, this is a breakthrough technology from Canada, so proud to so. And you will be part of our coordinating, we will send you a quarterly newsletter so you keep tab on what is happening. Timeline for the study. So you will have all the month of June to talk to your team, hopefully convince them that this is a worthwhile investment into the right to direct a new technology. So June 7th, that's obviously today, this is the informational webinar, and you will have until June 28th to reserve a spot into our 10 spots that we have reserved for this study at a cost of 15,000 Canadian dollars each. Again, this type of studies cost upwards of $100,000. The last one we ran was $150,000. So we're trying to keep it accessible, but integrate as many miners as possible. Then by August, we should expect the reception of all the ores at UBC, and that's where we are going to be doing the initial processing of the ores. September 2nd is when we start the study proper. And then next year, around May, we will report back to you in terms of what we discover for mineral liberation analysis using your ore. With this, there's a QR code for you guys to register. There's like a form with a whole landing page that provides this information and more, and just provides a way for us to contact later, and so we can discuss the logistics on how to engage with us for this study. Anything else, Jen?
And the study link is below there, rockburst.tech/ECO2-study.
Yes.
That leads you to the same page.
Yeah. So with that, guys, I leave it at that. We have 12 questions already in the chat. So Kyle, over to you. It's Q&A time.
Yeah, so there is a lot of interest. I think you've captured a lot of people's imaginations with this. So I'm going to just start from the top here and work our way down, but certainly lots of really good questions have come in. So well, I guess the first one is why using CO2 versus some other kind of gas?
Yeah, we analyzed different gases that we could use, and we ended up with CO2 because of its thermodynamic properties. It's sort of uniquely ideal in the temperature and pressure regime at which it reaches supercritical conditions. And supercritical is important because supercritical fluid is the state of a supercritical fluid, sort of halfway between a gas and a liquid, is the best state of a fluid you can get for permeation into porous media. So the CO2 has its supercritical state at around 31 degrees Celsius, so that not much above ambient temperatures, and at around 74 bar, which is very accessible from an industrial pressure standpoint. When you look at the other gases, they're either a lot higher in temperature or a lot lower, so you'd have to add a lot more heat or do a lot of cooling, and that would be a lot of energy. Another aspect with CO2 that's so important is around the supercritical point, very small changes in pressure and temperature can get a very large change in volume and density. And that we can take advantage of from an energy perspective. So as we optimize our system in the future, we can set it up so that we bounce back and forth from supercritical to subcritical, but not all the way down to ambient each cycle, thus saving a lot of compression energy because we're just doing a very small delta, but getting that volume and density change that causes the breakage.
Yeah.
Thus, CO2 seemed like the perfect working fluid, and also one that had been missed in the history of gas expansion breakage.
Yep. Okay, can we go with the next question? We have a lot of them now.
Yeah.
Jeez.
So starting sizes, right now that seems like quite small. How does it scale up? Have you tried anything with larger ones?
We've been limited in size by our prototype equipment, which is not that large. We could fit probably a 3-inch, say, rock into our alpha prototype, but it wouldn't mean much because we'd only fit like 1 or 2 in there, and then you don't get representativity of the ore because ore is so heterogeneous that you need to process a lot of particles at the same time to get a good representation of what that result is going to be. So we've tended to use smaller particles in our prototypes. The one aspect of that, which makes sense, is that grinding energy in traditional comminution goes up exponentially as the particle sizes get smaller. So actually targeting the smaller sizes allows us to also prove that our case for the most energy intensive portion of the mineral processing chain,
which is grinding,
just grinding,
not crushing.
Right.
You will actually use bigger crushes, big one, grinding, and you
Yeah.
go
However, our
You're kind
technology
of
should. Yeah, go ahead.
sorry, you're kind of flowing into the next question here is where does this fit into on the flow sheet, and what equipment do you think it could potentially replace? And then what throughput do you envision this technology could be capable of?
Right. Flow sheet would be, yes, replacing potentially SAG mills and ball mills as a combined unit. Potentially, it could be just a ball mill if you need or want to use the prior stages, like say you have an HPGR ball mill flow sheet, we could be looking at replacing the ball mill. So it could be a combination of say 100 millimeter size, 150 to 100 millimeter size feed, all the way down to final product. Or our earlier estimations are, let's go for the finer grinding where the energy is the most intensive. So sort of like the 25 to 20 millimeter or smaller, maybe even 10 millimeter feed. There was a second part to that question, Kyle. Can you repeat it?
What throughput do you envision this technology could be capable of?
Right. That is going to be the key question as we scale the technology. We haven't got there yet, although we've been working on it from a conceptual point of view for several years. We believe that we can make this work as modular units or pods that can achieve meaningful amounts of comminution, say 1 million tons per year, and then scale those by repeating the units. So it'll be likely, at least in the initial years of its rollout, modular units that can be scaled by increasing the number of modules. But I know that the largest mines in the world process very large amounts of material per day. And in the future, who knows? We may have to look at scaling this technology to the big plant scale, of which there are I think examples in industry that can support quite large throughput. So I think that our target right now is looking at like a 3,000 ton per day unit, which is about 1 million tons per year.
Great. And then so I think yeah, modular is certainly the way to go with something like this. What are the typical compressive strengths of each of these raw ores, please?
Oh, I don't have those numbers on the top of my head, but we've looked at the literature, and you can find that literature through searching online, and you can even find like tables of the different types of rocks and their typical compressive strength. Of course, rock is, like I say, every sample of even the same material of rock is going to have a different result. So you have to actually, when you do those kind of tests, you have to test a lot of material and then sort of average it out. And yeah, in general, we do realize that all ores or any porous solid media is much stronger under compression than it is under tension. Porous media will always break easier with less force needed under tension, and rocks are no different. And we've looked at the tables and realized that the range can be about 10 to 30. There's obviously outliers from that, but a good average range would be 10 to 30 times weaker under tension.
Okay. And that question actually came from our guy in Saskatchewan, Paul Lab. So I think we know how to get a hold of you, Paul, if you've got a lot more questions. And it seems you're quite interested in this based on how often you appear in the questions here. So that's all good. So a couple folks are really interested in this is in situ applications. So what have you given any thought to in situ applications? And also a question of how could it potentially replace blasting practices?
Right. Actually, today there are some cases where expansion of CO2 is used as a blasting mechanism. It's a lower energy, more controllable blast mechanism than high explosives, but still has enough energy to cause, fracture of large boulders and rocks. So sometimes in construction sites, when they have to remove, say, a large underground rock that's too big to move by heavy equipment, it has to be broken up. They'll use like CO2 canisters with liquid CO2 in that you put a pulse of heat into it, raises the pressure, turns it into supercritical CO2, and then it bursts out of a rupture disk, and the volume expands by hundreds of times, thus blasting the rock apart, but with a little less energy than high explosives, so you don't have rocks flying a kilometer around the site. So it is used for that purpose. I think there was another part of that.
Is the in situ applications. So have you given any thought to how this might be worked? Yeah, in situ.
Right, we have thought about that. For now, we're focused on looking at replacing comminution, because in the mining industry, that's where the bulk of the energy goes. Blasting is actually not the highest, sort of energy use. It's a high energy explosion, but it's not where the bulk of the energy consumption. Thank you,
yeah, we're trying to address, like the main pain point in the mining industry would be energy efficiency in comminution. So that's where we have the most bang for our buck, literally.
We have thought about the fact that it could potentially be used for an in situ process. In fact, in some other areas of industry, a very similar approach is used, where you pump high pressure CO2 into the supercritical state underground, and then you do a rapid depressurization to fracture underground, a different type of sort of fracking than is typically done in industry. So you can look that up in the literature online. And yes, I think there's potential for our technology to go in that direction, but much further down the road.
Great. You guys certainly know your stuff. You're able to answer all these questions really, really easy. This is great. One other question here, and I think it's very important, particularly for the mine operators, is, they want to keep their mineral properties to themselves. There's a confidentiality issue there, some kind of intellectual property as well. So if they were to decide to participate in this study, how is that going to be kept confidential? How is all that information going to be kept safe?
Yeah, so the idea is, to have, as I said, two types of report. One that is, all the information for the participant, and one which is a collated report with anonymized data. So only identifiable by mineral and, what we observe as a mineral liberation analysis. So we will have to work with them really, to really understand what they want to share with others and what they didn't want to. So absolutely, we have to be obviously flexible in that sense, because some of them have different ways of looking at it, but the idea is, to obey whatever policy they have in place.
And just to be clarified, the report that's for each participant is only to the ones who send the ores.
Yeah,
so it's not going to be shared among.
Yeah, exactly. Fair. Yeah, exactly. Only the ones who will share ores, will get a report, and is the collated version of it.
Yeah, great. A couple more here. So as a dry comminution process, have you considered a drying stage before? And do you have a sense of what the costs would be for that?
Well, actually, we've been looking at it as though we would accept wet material. So if the material is in a stockpile and it's wet, or it's in the north and it's got snow and ice mixed in with it, we're basically going to allow for that material to come into our process. We find that we may not want to, introduce a lot of water and keep it mostly CO2, because we want to save on the water use. However, we know from tests that our process does work with water. So we think it's actually a benefit that we don't have to dry and spend energy on drying the material before it comes into our process. The amount of water that would come in from during the loading of the raw material is not going to be a problem of degrading our process. So that's going to be handled.
Great. Less of a question and more of an offer of support here. So Don is the new CEO of Rethink Mining, which I think you folks may be aware of, and certainly we are here at MICA as well. So there's a little bit in there about how they supported companies in the past to form consortiums, and certainly this has worked in a number of in a number of instances. And in fact, we're also working with another company, Rhino, who is also working with Rethink Mining and has had great success with their consortium approach. So Don's kindly put his email in there, and if you want to reach out, I would recommend, because of course any support is good support, and they have also worked with a number of mine operators as well.
Absolutely.
Don,
Thank you. Thank you, Don.
thank you for the offer, and glad to see you're here. You've been on my list of folks to reach out to, so maybe I'll follow up after this as well. So thanks, Don. Paul, you will get a copy of the recording. Cedric Laney from Valet, do you see a combination with microwaves treatment? Would that provide any benefits?
Yeah, we have looked at pre-treatment for ahead of our process. And so one thing that's worth even mentioning before getting into that is that our direct tensile breakage process is an absolute replacement for final comminution, even down to very small sizes, maybe even down to ultra fine grinding. So we are not just a pre-treatment, where a lot of other new technologies around tensile breakage are considered useful for pre-treatment, and microwave, I think, is one of those. It looks like it could be valuable to reduce the energy in the milling processes, but really as a pre-treatment, if you have to go all the way to using microwaves to break the rock to final size, it uses too much energy, apparently. This is what I've sort of learned from talking to others in literature. So but for us, what could be advantageous, however, is a low energy but microwave pretreatment that introduces microfracture in the rock, especially in, say, a very hard, maybe low porosity rock that we want to process with our CO2 pulverization, introducing microcracks and then putting it in our process to take advantage of those cracks to fracture the rock. And that could be a very advantageous flow sheet. And we would love to study more about taking microwave pretreated rock, and we have some we've been holding ready to test with. We just haven't got to it yet in the lab. We will get to it shortly, where that material had been pretreated by microwaves. So we think this could be a very preferential chain, and we have to study it a little bit further. But it's a very good idea and a good question.
Great. Last one here. Wondering about the source of CO2 that will be used. And is this technology dependent on high purity carbon sources captured from the air, and how big is the cost of CO2 capture per ton ore?
Right. We are definitely looking at in the future, as this scales up and goes commercial and is deployed in mining sites, to use captured CO2. And we want to avoid, obviously, any fossil sources of that CO2. And so capture scenarios are going to be point source capture, like from flue gas or other process emissions, and or direct air capture. And those industries are rapidly progressing. The point source capture industry has been around for a long time. And if you have enough concentrated feed from, say, a combustion source, the price per ton is already not that high. Those tons of CO2 are all, sort of well below $100 per ton, and not in many cases they're below 50. The direct air capture industry is a nascent industry, currently quite expensive per ton, on the order of, I think, $600 to $1,000 a ton today. But the projections are very for rapid decline over the next 10 years because of the, being driven by the climate need. And so we think that as we're starting to roll this out commercially, that is also going to be a crossover point where we could access direct air captured CO2 on site at a cost that will be more than suitable for our needs. Our models so far have been using prices around, well, in our latest models, $1,000 a ton, because that's kind of what you can get from current direct air capture. And it still works. So we don't use necessarily a lot of CO2 in the projected future systems which recirculate it. We only have a lower amount of losses. and or we can drive sequestration. So that may be a valuable sort of output of CO2 from our process, which is it's locked up into the rock. And we may be able to tune how much is either locked up into the rock or just used in our process and recirculated. But at every stage, we're going to look at reducing the amount of atmospheric losses.
Perfect.
I think it was another part to that question. There was 3 parts. I missed one.
The cost of CO2 cap. I think you're good though.
Okay.
I see.
Oscar,
Sorry, Carl. Just want to mention there's a question about the applications for in the cement industry, and I'm kind of sad that we didn't see Lafarge and Holcim here and any other cement folks here. Absolutely, that's the other industry that we're looking at to deploy our technology as a pilot. If, and this is a big if, but if we could deploy a potential pilot in the cement industry that is capturing CO2 from their own operations, we could use that CO2 to run comminution systems for their limestone and clinker. And they need dry comminution, which is done by default in our process. Right. So that, out there in the audience, if you're looking at a virtuous cycle with our technology that we could potentially engage as a partnership, by all means, reach out to us. That would be a fantastic. It is really the next generation of hard tech or industrial technologies where you're able to use waste something to exert some sort of work, use that waste and convert it into value. This is, if this technology scales up, the way we want it, obviously, is poised to do just that. Not only in the mining industry, we have considered, as I said, applications in the cement industry, but also extrapolating, the critical minerals area all the way to electronic waste recovery for the same purpose. Again, we're able to delaminate from within, break rock from within, and therefore delaminate. So that's another aspect that we are very, very curious about testing in the future, just so you guys understand, the consequential impact this technology could have. Fingers crossed.
Yeah. So don't let me forget, Oscar. We've got a cement manufacturer here locally in Sudbury that is he's very open to ideas. So send me an email to remind me to follow up.
Absolutely.
And then there's one here about the range of compressive strength of successfully tested materials so far, 30 to 200, I think it's megapascals, MPa, testing the limits of my science here. But there's no obvious limits for that harder rock would not work for TCO2 pulverization. I think.
Right. Yeah, I think I would agree. There's no limitation for TCO2 to break even very hard rock because we are taking advantage of those preferential physics for tensile breakage.
Great. And so that's the end of the questions here. So thank you guys for your time. But I think Oscar and team, just again, reiterate what the study's about and how to get in touch with you. How do they take part? So just one more time.
Yeah, for sure. Once again, what we are running right now is a mineral liberation analysis. It's a crowd-funded approach. So, we're decreasing the cost so we can increase the number of participants. We expect up to 10 ores. It could come from one company or 10 companies. It doesn't really matter. But 10 ores is kind of our operational limit, charging $15,000 per ore. Once again, this is like a tenth of what it will cost us to do it just once. And you can see the timeline right here on the screen. So you will have until June 28th for registering with us. So with that, you can go to the web page that appears right here on the screen, or you can scan that QR code. It will take you to the whole landing page. And at the bottom of the landing page, there's a registration form that you can send out to us. We will contact you afterwards, to basically deal with the paperwork and that.
And I just wanted to add one more little final piece, and that is as part of the study, obviously, to get to being able to do mineral liberation analysis, we're doing the comminution.
Yeah.
And so you're going to get some results preliminary results on comminution performance of your material, as well as then the lab-based mineral liberation analysis comparison between baseline incumbent milling and our pulverization technology. So it's going to be a really good comprehensive data result.
Yep.
Awesome. Well, thank you again for taking the time to tell us all about this fantastic technology that you guys are developing. Appreciate everyone who tuned in online for your time this afternoon, morning, or evening, wherever you guys are calling in from, to learn a little bit more about RockBurst Technologies and the study that they're undertaking. And again, us here at MICA, we're very very enthusiastic about the technology that they're developing, and hoping to see a successful study here with McMaster University and other partners. So again, if you're interested in participating, the link there is in the chat. It's available online. You can find it on LinkedIn, all sorts of places and ways to get it. And there's a registration form at the bottom of the page. So yeah, thank you again for tuning in. And we'll be following up with the recording and some other materials. So if you registered, you can expect to receive those in the next early next week. That's what I'll commit to. All right. Thank you very much.
Kyle. Appreciate it. Thank you,
Appreciate it.
guys.
Thank you, everyone. Thank you, Kyle.